We're doing number 1 on the quiz. The temperature in Celsius of 1 kilogram of lead. So we can do this at 1,000 grams. So this would be T initial, and I think it does TIs in this and not T sub O. After it falls 200 meters. So given this, after it falls, we're looking at the potential energy is going to go into heat energy, which would be MC delta T. So this is going to be mgh is equal to mc delta T. Right? I think that should pop out of there. That'll pop out of there. What else we got? Okay, so we can do, what does the acceleration do to gravity at the student's location? Okay, so we have this equation, 2 pi times the square root of L over G. So if we do this period, we want this in seconds per revolution or oscillations or something. So we can take this, convert it to seconds, divide by our 50, and that should give you T. And then once you have T, you can square both sides and solve for G. So this is going to be 120 and 54. That's going to be 174 seconds. 50. Complete vibrate. Yeah, 50. That'll give you seconds per vibration, or I don't like the term vibration for that. 50. Why isn't this? Wouldn't cycles make more sense for a word? Going back and forth? Yeah, I think so. What else do we have? What's that? Maybe. Homework. Okay, yep, I'm ready. 17-13. Let's see. Is this... Okay, so this is a closed pipe. If this is a closed pipe, F to the N equals N V over 4L, I believe. I am just a fog brain right now. Closed pipe, closed pipe, yes. NV over, yes, NV over 4L. So remember, what you could do for a closed pipe, and this is where we're starting again. You know, you can always draw this, right? And when you draw this, you could do this if you're, you know, to give you an idea, and then come up with another counter wave like this. Oh man, that's almost spot on. I don't know how many I did. Okay. Now, this is what we left off doing. We said that this is our fundamental, and that's 1/4 of a wave, right? That's our fundamental. This is our first overtone. Three-fourths of a wavelength. And so on. The next one, if you cut the pipe, this is where you'd have to cut the pipes, right? If you cut the pipe right here, you'd end up with 5/4 lambda. And then the very last one, since I've got it drawn out pretty dang good, this end right here would be 7/4 lambda. Did I do that right? I did. I just drew it out. I ended perfectly. My day is getting better. Unless I die of the shingles vaccine tonight. Good knowing you guys. Now, this is the fundamental. First overtone, second overtone, third overtone. So it wants the fundamental frequency. So this is n equals 1, n equals 3, n equals 5, n equals 7. These are the numerators here. Oh, good review on this. These numbers are the numerators. Then the frequency would be given by this. So this n equals 1 is the fundamental overtone, third overtone. It wants all of them, doesn't it? They're asking for a frequency. Okay? And realize we would change the frequency here. You're not going to put the same frequency in there. So for example, so here's your lab apparatus. Tomorrow this is full of water. So where am I at? Now when you raise this up, the water level inside there goes down by the volume of the pipe, right? So $440. I'm looking for some. Oh, somebody's using their boot like weighed a ton. Paper towels or something like this works good. So the first resonant hum is going to be the fundamental. So this should be 1/4 of a wavelength, right? Now when you measure this tomorrow, you're going to measure inside there from the top of the water to the top of this, and you'll get it. Now, so that's the fundamental. Actually, I might be off. This is probably the fundamental. This is interference, might be interference from the inner pipe. I think that's the first one right there. There's the second one. What's the distance between those two? Always is a half a wavelength, right? Half a wavelength. Now, the first one down here, 1/4 of a wavelength, 3/4 of a wavelength, right? 3/4 of a wavelength. Next one is going to be at 5/4 of a wavelength, right? Now, but in this problem, you would have to, that's a fixed pipe. What is the size of that pipe? It's a 20 centimeter pipe. So you have to change, let's say this distance right here, well, that's about right. If I cut that off, that first one was at about 20 centimeters. And I can only get, with 440 hertz, I can only get 1/4 of a wave in there, correct? So if I want the fundamental, the next one, which is 3/4 of a wave, I can't use this. I have to go to a higher frequency. When I go to a higher frequency, then I should be able to get 3/4 of a wave. Because remember, I can't change the length, right? So every time, if you use a fixed pipe and it wants the fundamental, that's 1/4 of a wavelength at that certain frequency, If you want to slam more waves into that fixed length, you got to go up in frequency. So for this, did you smile, Jesse? So the fundamental, we put a 1 in here now. We got 20 degrees, so we'd have to calculate the velocity of sound at 20 first. That's going to be our V. So this V right here is going to be 331 meters per second plus 0.6 times 20. That's going to get me another 12. So it gets me another 12. We're at 343, right? So the fundamental at that length, fixed length pipe is going to be 343 meters per second over 4 times 0.20 meters, 20 centimeters. And what does this fundamental, I should put an F1 here, I apologize. This should be a 1. So if that's a 1, what do we get for this first one? 428. Is it 429?
Yeah.
Okay. Now I change this to a fundamental. All I got to do then, F3 is going to equal to 3F1. If I just put a 3 in there. So 3 times that is going to be 1297. 87? 1287? 1287? And then you could put a 5 in there and a 7 in there. But again, in our experiment, we'd have to change tuning forks. We'd have to go from 429 to 1287 and so on. Now, some in the lab today grabbed 1,000 hertz. So the lab, I just say do a 200, do a 300, do a 400, do a 500. Well, somebody grabbed 1,000. And when you grab 1,000, the first one is about 8.5 centimeters. And their error was kind of large because, you know, if they've got this pipe in here tilted and they're measuring the height of the water right there up, and they had a pretty good error. They lost a sig fig too, right, if you're under 10. So try to do 200, 300, 400, 500 per mile for lab. Well, I couldn't ask for a better question to review closed pipe resonance. All right, and that's a pretty good review. 1/4 of a wavelength, 3/4. The distance between these is a half a wavelength, right? So what else do we have? Okay, let's fix this baby up. Because this baby right here is what you're going to want next week, Thursday, right? Yeah, Thursday. So we've got all this inside 1. Inside 2, I don't know. I put this on here. This is the coefficient of elasticity. Did we put that up here in this class? No? Yes? No? All right, so let's add that to the back side or however you have it. Then starting tomorrow, we're going to work on torque and rotational motion, so we'll use that. Otherwise, on the top of this, let's add this. Let me focus that. Good to cross out this. Good to move this up. No, yes. 1 second. We didn't really use this equation. We used 331 plus 0.6 times degrees Celsius. You've probably seen that enough now. I think this will finish us off. And I think that gets us where we're at right now. So again, we're going to go backtrack, do a little bit of torque, then we'll be finishing up, right? But you're going to want to have this for your test. Okay, let's go to, we left off right here. Boy, I hit a home run with this one. Oh, that's refrigerator art if I ever saw it. That is nice. We have to do, it looks like we got to do B. So it looks like this, where the frequency of its fourth overtone. Now remember, is you want to look for this right there. If it's closed, you want to go up by odd numbers, right? So we're going to go 1, 3, 5, 7, 9, 11. I don't know. This is the fundamental, right? This is the first overtone, second overtone, third overtone, fourth overtone. So we're going to use 9 in here. And you can put a little 9 down here to represent then fourth overtone. So again, it's the same length pipe. So if it's the same length pipe, we got to slam a much, much higher frequency in there, correct? Much, much higher frequency. And if F1 well, we'll just put it in here. F9 is going to be 9V over 4L. My velocity is 344 meters per second divided by 4 divided by 0.672 meters. So we should get the same as 9 times 128. We're going to get what? 11 something? right around 1200. $11.51. The other way to do this is to say F9 is equal to 9F1, and that would also be 1151 hertz. Okay. So what are the frequencies of the fundamental? F1, F3, and F5, right? Fundamental F1. My pipe is going to be 0.12 meters. My air temperature is 30, so my speed should be 331. That's going to add 18. We're going to be at 349, right? Well, then F1 is going to be 1 V over 4L. Now, for tomorrow's lab, make sure you got everything in meters. So this is going to give us what? $727? Is it around 27? No? 727? Oh, it does say it right here, but maybe I typed that in wrong. Maybe I tried lying to you. So F3 is going to be equal to 3F1, and F5 is going to be 5F1. And 36, 35. Who's the musical instrument expert? You can take all those musical instruments, you just unwind them, right? Uncoil them. So you get a straight pipe then, for the most part. Trumpets angled, right? Some of those brass instruments. If it doesn't have a reed, so you could uncoil a trumpet. What else? Tuba, you can uncoil a tuba. Make one straight pipe, right? So if you got a tuba or a trumpet you don't want, bring it in, take it down to the welding guys, and heat it up, and we see if we can straighten it. Okay, so that's closed pipes. Again, it goes up by odd numbers. And if you have a fixed length pipe, you got to slam higher frequencies in there to get more waves in that fixed length pipe. Higher frequencies, right? So this is an open pipe. So for this open pipe, I will attempt this. I'm probably going to, ooh, I can see underneath. Look at that. Ooh, I can do this now that I can cheat. Oh, in fact, it does work backwards. Well, I needed to stop right here, so I messed up. For an open pipe, let's stop right there. Let's see, I'll make this a little bit better. Maybe cut that off. It's white out. So this is your resonant lengths for an open pipe. We cut it right here. So these are antinodes, these are nodes. Nodes, 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 where they cancel. Constructive interference. And antinodes. So they say that an open pipe has antinodes at both ends. Well, on my fundamental right here, how much of a wave? It would be a quarter to here. But you have a quarter and you have a quarter, so we have a half a wavelength on the first one. The second one's easier to see. What's on the second one? Second one's a full wave, right? Because you'd start repeating yourself right here. So this is 2/2. If we had a pipe this length, how many wavelengths are in there? How many wavelengths are in there? 1 1/2, right? Because this is a full wave, correct? This is a full wave, this is another half. So if I did 1 1/2, I could go 3/2 lambda. Now you see the pattern. 4/2 lambda, which would be 2 full waves, and then 5/2. Since you do not start out at a quarter, you go up by halves. And these go up by ones for an open pipe. Instead of odds, right? So that's the very first thing you want to determine. Do you have a closed pipe or an open pipe? If you have a closed pipe, all of these go up by odd numbers. 1/4, 3/4, 5/4, and so on. If you have an open pipe, these go up by ones. So basically then, we have the same situation here, but the fundamental is going to be a 1. The first overtone is n equals 2, and n equals 3, and so on. Again, you just go up by ones instead of odd numbers. So, what length of open pipe will have a frequency of 1200 hertz at the first overtone? So you have 1200 hertz. How much of a wave do you want in that pipe? So at the first overtone, this is going to be the fundamental. This is going to be your first overtone. How much of a wave's in there? You got a full wave in there, correct? So you could take it that way and calculate it. That pipe has to be 1 wavelength long. So 1 wavelength is going to be my velocity, 340 meters per second. That would be divided by, divided by the frequency of 1200 hertz. Oh, man. So that would be the answer, right? 283 meters. Or, if you plug the formula, we would do this. We would say F2 is equal to N V over not 4L but 2L. But N equals 2 right here, correct? So F2 is equal to V over L. And we're going to have the same thing I got up there. I'd cancel out my 2's. So I'd end up with the same answer, 0.283. Okay. This right here shows, no, this is a vibrating spring, closed pipe, open pipe. And the only thing that you may get a question is a beat frequency, and you just subtract the 2 frequencies. That's it. Beat frequencies. Beats are regular pulsations in intensity that occur in presence of 2 sounds of slightly different frequencies. So you would just subtract the 2 frequencies, and that would give you your beat frequency. And it might be as simple as 340 hertz minus 350 hertz, or 350 hertz minus 340 hertz. It's 10. Okay. That finishes up 17. If you have not printed the lab, go to Canvas. And it should be here. This is Lab 11, speed of sound. Download that pig. And then here's the spreadsheet. Now, I'm just shocked a little bit about, we got students now that haven't used Excel. Is that because they're using Chromebooks now, or schools are doing I don't get it. So I left the formula in here to calculate your average. But then you're going to calculate these. I would put the formula in. You know, teach each other a little bit of Excel. Here you've got a radius, here you've got a temperature. So teach each other a little bit of Excel. If I go to the lab, again, 4 tuning forks, 200, 300, 400, like this 400, 200, 300, 400, 500. Tuning fork's going to look like this. So this is the fundamental, first overtone. And then there is a correction factor for the radius of the tube. So the fundamental is not just 4L. It's 4L plus 0.61R. And then the second resonant length has a correction factor as well for the radius. So you're going to easily measure those two. I showed you how easy it is to listen to it, correct? You're going to know L for both of these. The first hum here, you're going to know the radius. You're going to calculate the wavelength. You're going to measure the temperature of water, which hopefully they're sitting with water in them right now. Some leak. It should just be room temperature. So your velocity is going to be based upon the temperature. So that's going to be about 340. This wavelength right here. Or excuse me. We're not going to assume this is 340. Sorry. You've calculated your wavelength, and you know the frequency of your tuning fork right here. You're going to use this wavelength calculation times the frequency of your tuning fork to see what you get, and you should get close to 340. Okay. And then there's 5 questions. Everybody got it done and submitted, I believe, this morning. So there's what it looks like. So we'll get the pennies out tomorrow. We'll get the lab going. And away we'll go. So we're done. We're bubbling. We're bubbling Friday, right? We're starting torque for you guys. Rotational motion and torque. Not tomorrow, but Thursday.